register. Got it. Okay. So, good morning. This is beginning of our morning session. We start with a small delay due to technical problem, but it is better to start later than never. And this is really a pleasure for me to introduce the first speaker, who is Professor Nikolay Tzvetkov from Cergy-Pontoise, who will speak about the transport of Gaussian measures under Hamiltonian PDEs. Please, Nikolay.
Thank you very much, Vladimir, for the invitation, and especially coming from you. I'm very pleased and happy, and as many people maybe know, I am doing PDE thanks to you, and actually I think I'm doing research thanks to you, because when I started to study mathematics, it was in Bulgaria in very difficult situation, and I was very happy that people like you were helping young students in Bulgaria, and so I was really happy to be able to work with you. And so actually it was you who explained me what research in mathematics is, because at the time I was student in University of Sofia, most of the active researchers were abroad, and I was really fortunate that somebody like you was still in Bulgaria at that time. It was one of the most difficult time of our country just after the communist period, and really I am always grateful to you. Without you I wouldn't do mathematics, that's for sure. So I'm also very happy that I see in the audience some Japanese mathematicians, and especially Professor Ozawa and Professor Yajima. I would be happy to see them in person, but unfortunately with this crazy situation we can just see in this way. But I'm really honored to see that they are in the audience. And of course I see other people. I don't know who is in presence, but I know that there are some friends there. So I'm really sorry not to be in Italy at that time, which is the most beautiful country from my viewpoint. Okay, so today I will talk about a topic which is maybe many of you are not familiar with. So I will try to give a not so technical talk. And these kind of problems are related to invariant measure problems, and also maybe seen as a kind related to propagation of regularity in a more refined way. It also can be seen as a problem of solving transport equations in infinite dimensions. So I will try to be more precise on this. So I am studying these problems since 4 or 5 years, and I did several joint works with various people. They're all mentioned here. And if I see correctly, there are at least 1, 2, 3 Italians in the people I was fortunate to work with. And also people from other countries. So the names are written in my slide. Of course, I will not have time to present all these works. I will more try to give some explanation what is the kind of results we obtain, and I will probably concentrate a little bit in more details about the results which were obtained with Fabrice Planchon and Nicolas Vichilia. But I will also mention some other works in the field, so I will try to do it accordingly during the talk. So what is the Gaussian measures I will be care about? So the Gaussian measures I will care about are related to Sobolev spaces on the torus. So that's why I will first start by recalling what is the definition of the Sobolev space on a circle. So I recall that the circle is defined like this, and we will denote by H's the Sobolev space of the circle, and I will briefly recall what is the Sobolev norm, because this is what will be important for me. So if a function is developed as a Fourier series, and maybe it may be a distribution, of course, because the Fourier coefficients are defined essentially for any u, which is in the duo of say infinity, and they are defined as the integral of the function against the exponentials, the characters. And so this is a complex number. Of course, if u is not a function in the distribution, you should define this integral, interpret this integral in the usual way. And so we can develop a function as a Fourier series, and then the Fourier norm, the Sobolev norm, can be expressed in terms of the Fourier coefficients as it is written. When I showed the line with do you see what I'm doing now? Vladimir.
Yes.
Yeah, okay. So the Sobolev norm is defined like this, and as you see, it's expressed uniquely in terms of the modulus of the Fourier coefficient. It depends only on the modulus, actually. The phase of the Fourier coefficient is not important. And of course, there is the important parameter S in the definition of the Sobolev norm, which measures the regularity of the function. And this notion n to the power 2s is, as usual, the Japanese bracket. So now I recall what is the Sobolev norm. So the important thing for me is the expression of the Sobolev norm in terms of the coefficients. We can wish to define the Gaussian measure, which is based on the Sobolev space HS. Okay, so now I know what is the Sobolev space HS, and I would like to define a Gaussian measure, which is a formal object. So we wish to define an object of this time, exponential minus UHS squared du. So this should be a probability measure. That's why I put this z minus 1, whatever it means. And I would like to define it as somehow exponential minus the norm in HS to the power 2 times du. So the problem here is that u is living in infinite dimensional space. And in infinite dimensional space, du, unfortunately, doesn't make sense. We don't know what means the product of infinitely many Lebesgue measures. Why? We don't know, because the Lebesgue measures are not finite measures. And so infinite product doesn't make sense. So that's the problem. But if it was a finite dimension, for example, if u was in dimension 1, and then UHS square in dimension 1 is just the usual distance in R, then we really see a Gaussian measure as far as we choose Z so far that the total measure is 1. So we really have a probability measure. So in dimension 1, we see how to define this object. Even in dimension 5 or 10, we can do it. As far as the dimension is finite, just this HS square will be replaced by some finite dimensional norm. And then finite dimensional norms, we can make some nice transformation and really see it as a higher dimensional Gaussian measure, as far as Z is chosen to make it of measure 1. The problem is in infinite dimension, what to do. And so the nice thing is that this HS square norm has a very nice expression in terms of the Fourier coefficient. And so formally, I will take this expression, Z minus 1 exponential minus UHS squared du. And when I take the exponential, I will replace HS square by the definition. It is sum. Of course, the minus is important because it makes the exponential small. Sum over the z of n to the power s u hat square. So this makes sense, okay? And then du, how I interpret this du, okay, because I think that each function somehow is, it's completely determined by the Fourier coefficient. So I can try to say that this du is the infinite product of the Lebesgue measure on each coefficient. So this infinite product of Lebesgue measure, as I said, is not defined. So this is again a completely formal, object. But if for some reason this exponential goes after the product of this exponential, and then the good thing is that the exponential of sum of two things is the product of exponentials. And so the last expression, I can write that this exponential of minus sum is actually the product of all exponential of minus n to the power s u hat square. So du I keep it. And now I do something which is very important. I forget this z minus 1, which is doesn't make sense either. But for each fixed n, I put the corresponding Zn to the power minus 1, which now is a completely determined number. We can compute it. It depends on n, but it's just this integral, which now is done in 2 dimensions. You know, exponential minus n to the power 2s u hat n squared du hat. So this is a 2-dimensional measure. This makes sense. And you can even compute this integral and say it's some number which depends on n because of the dependence of n here. And I put it to the power minus 1. So what is after the product is now completely well-defined measure on R2, or if you prefer, on the complex numbers. And then what is nice is that Kolmogorov, in the beginning of the 20th century, proved a theorem saying that if you have infinitely many probability measures, but probability measure, it doesn't work for the Lebesgue measure on R, and then you can define the product of infinitely many probability measures in such a way that there is a unique infinite product measure which satisfies the natural properties that if you restrict it to finite dimensions, then it is the measure is doing what you wish. I mean, it coincides with the finite dimensional measure. So this is a very important theorem of Kolmogorov, which is saying that, okay, we cannot define infinite product of the Lebesgue measures on R, but infinitely product of finite measures is okay. And so now, as you see, I did the 1, 2, 3 lines, completely formal computations. But this line, I write something which is perfectly well defined, mathematically perfectly well defined. And so this is the measure that I will call which will be the Gaussian measure, which is written in the first line. So as you see, I start with something formal, I make some computations, and then in this almost last line, so what I'm now showing is well defined, and this is by thanks to Kolmogorov. Okay, so I'm using a black box, and so now this is the measure for me. So I say that this infinite product measures defined then thanks to Kolmogorov is the Gaussian measure mu s. This is the definition, and as you see, what happened with I even computed Zn. So Zn is this number, Pn to the power minus 2s. As you see, if s is positive, essentially this is infinite, right? This is infinity somehow. The product, there actually no product is convergent here. I mean, this is constant z, nothing is convergent. But what makes sense is the product of the infinitely many measures. So this is a delicate procedure, right? So being familiar with this procedure already requires some effort. And so we define like this the Gaussian measure. Since I know, actually, I spent time with this slide because I know that if you are not familiar already here, there is something to be deeply understood. And what will be somehow cheating in the intuition of the problems, we often use the definition which is written here in the first slide. I mean, in the second line of the slide. So we should keep in mind this definition, but when we do rigorous work, we cannot do it. And that's somehow the challenge, that we follow some crazy intuition, but then you should justify it. And as happens often, it's not so easy to justify it. And sometimes it's even wrong what the naive intuition is saying, or not clear. So somehow it's a frustrating field because quickly you can do some formal computations, and then quickly you are frustrated that your formal computations are not so easy to be justified. Yeah. So this is now. And now, actually, I say my measure mu s is defined as this product measure. But actually, it will happen that there is a nice way to see this measure, and this is the way I use it most often. Actually, we can see this measure as actually a random variable with values in some Sobolev space. Okay, because in the previous slide I didn't justify on which space is my random variable. Actually, it's in some very crazy space. What is nice here is that we are doing PDE. It will be possible to see this measure as the distribution or as the law of a random variable with values in some functional space, which of course is equivalent thing because any random variable, its law is a measure on the image space. But of course, it's important what the image space is. And so here we will identify some concrete image spaces, which are also Sobolev spaces. And we will see this measure defined in the previous slide as the image, as the law or the distribution of these random variables. So this is actually saying the same thing, but if you prefer in more concrete way, something which you can start to do computations and things like this. It's not just Kolmogorov theorem is abstract thing, which is nice, but then when you start to do computation, we prefer to have some more concrete things. And so that's what I will do now. I will define the Gaussian measure in a concrete way. So what is this concrete way? So we can say that in fact the Gaussian measure we defined is the image measure by the map, which to some omega in some probability space gives the random series, which has as a Fourier coefficients gn omega over n to the power n to the power s, where gn omega are identically distributed complex Gaussian random variables with mean 0 and variance 1 on some probability space. So why this is the same construction? Because if you want, I just see the function, as I say, we can identify the function with its Fourier coefficients. So somehow in the previous slide, it was the product where on each Fourier coefficient, I put some Gaussian with variance, which is of mean 0 clearly, but which has some variance, which is n to the power 2s, which actually is depending on the Fourier coefficient, unless s is equal to 0, which corresponds to the white noise. And in fact, I write the same thing here somehow. I just say that on each Fourier coefficient, I put a Gaussian variable. And what means that they are independent? What means the independence? But the independence is simply the fact that it was a product measure, right? Actually, independence for people, this is the definition of independence, right? When you take the law of the couple, it's the product of the laws. So that's why I say independent. And identically distributed, they are because I normalize by this n to the power 2s. I can, of course, put here gn omega without n to the power s, but then each gn omega, they will be still independent, but the variance will be different. And now I normalize the variance to be 1. What means the variance 1? Just this n to the power 2s, I rescale it to 1. What is here? And so if I rescale it to 1, the price to pay that I should divide the normalized random variable by n to the power s. And so this is another way to define the Gaussian measure, which is more concrete. Actually, I see it as the image measure by this map. And now actually the good thing with this view of point is that I can identify the image space, because actually what I write is not completely rigorous, because I can of course say the image space are the distributions and it will be rigorous. But what is nice is that I can choose it. I have a lot of choices and I can choose it, and then I really work with this space as the space where the measure is defined on, and I have a true freedom, you know. That's something specific to infinite dimensions. In finite dimension, if you define the random variable on R, on Rn, you don't change Rn, Rn stays Rn. In infinite dimensions, I really can choose the space, and that's my freedom, and it can have some importance. It has some importance. And so that's why I raise the question. This measure is defined on which space? And in the next slide, we compute a possible space, not any possible space, but one possible space is actually some H sigma. So people, actually, the first time I studied these things, it was still in Bulgaria, I remember. It was some professor in Sofia University was explaining this construction. And when I was a student, my first belief was that, okay, but this measure exponential minus UH squared, what I try to define this, it should be a measure on HS because I start by HS, I try to compute, and then why it shouldn't be HS, the space on which the measure is computed. And you see now the explanation. The explanation is here because, in fact, when I try to define this measure rigorously, in fact, I should show that I should see whether this kind of random series, which define the support of the measure, leave. And if I compute their H sigma regularity, so sigma is something free. So there is a small computation which says that if I take actually the partial sums of the random series, which is supposed to define my measure, when I compute the H sigma norm, as you see, first we compute the H sigma, then I take the expectation, because there are two parameters now, X, which is the usual parameter, and omega, the random parameter. So there are two now. And when I compute the H sigma norm, as you see, so there is a very small effort normally for all of you to see that the H sigma norm here is sum gn omega square n to the power 2 sigma and divided by n to the power s. So gn omega is there. And then when you make the expectation, it means the integration in omega, integral of gn omega square is 1, because I normalized my Gaussians to be a variance 1. And so integral of gn omega, gn square disappears. And so this is really equal. So this L2 omega with values in H sigma is this sum. And now you see that if sigma is equal to S, it's a big trouble because it doesn't converge. I just sum 1 many times and this series doesn't converge. And if we would like that make that this series converges, then of course I should impose that sigma is smaller than S, and actually the precise condition on sigma should be sigma not only smaller than S, but smaller than S minus 1/2 if I would like to make converging this series. And in fact, therefore, this computation is just saying that my random series of the previous slide is object which is in L2 of the probability space omega with values in H sigma. So this is a function space, right? And so now what we can do is that say that in fact this space L2 omega with values in H sigma is a complete space. And in fact, and therefore this can be defined as an object there. And so since we have function which is in L2 in omega with values in H sigma, it is also a measurable function. Measurable function from omega to H sigma. You know, now the infinite dimensional object is this H sigma, which as you see is small, much bigger than HS, because sigma is smaller than S minus 1/2. And this is the place where my measure is defined on. My measure is on this space, H sigma. And why it is a measure? Because it is an object in L2 omega H sigma. And in particular, I don't care of the L2 omega. I care that just it defines a measurable map, you know. And the important thing of the fact that it was a Cauchy sequence is not so much that this is in L2, is that it defines a measurable map in the sense of the measure theory, which means that the inverse of Borel set in H sigma is in the sigma algebra on the probability space. So here I do something rigorous and I define this sum as a random variable on H sigma. That's what I say in this slide. So therefore, we conclude that this map defines a probability measure on H sigma. And in fact, but which is sigma? Sigma is not S. Sigma is smaller than S minus 1/2. In fact, we can show that the probability of the actually HS minus 1/2 is of probability 0, is of measure 0 with respect to the measure mu S. So it means that really the Hilbert space HS I started with, unfortunately, is of measure 0, or fortunately, but this is what happens. In this construction, the space HS is canonical because I started from the very beginning by exponential minus UHS square. In this place, the Hilbert norm was canonical, but H sigma is not. For instance, it can be replaced by the Sobolev space W sigma infinity, which is even larger, right? Because I require sigma derivative if an infinity, which of course is, if this is true, it will be also in L2. And this is also a good space in the sense that, of course, I should work more. I don't have such small computation just as in the previous slide, but one can do some computations and justify that this as a support of the measure, as a probability measure on this space 2. So as you see, it's not canonical. For my purpose, H sigma will be okay, but I keep in mind that there are possibilities. And even with this space W sigma, I can similar properties. For instance, WS minus 1/2 infinity is of measure 0. And then to prove this one, you need to use some not so easy things, not so trivial things like, it's a bit technical, but even on the scale of the W sigma infinity, you have similar discussion. It's a little more involved. The fact that the probability of the measure of HS minus 1/2 is 0 is very easy. In fact, it's a relatively easy exercise on infinite products. With the Sobolev space, I don't know so easy proof. I need to use some more involved techniques. The independence should be used in a more involved way. I would do it. I would say it like this. And of course, I don't have time to enter in this detail. So, okay, now the measure is defined. And the question which I will study in my talk is how this measure behaves under transformations. Of course, the behavior of the measure under transformation, it appears in many areas of mathematics. In PDE, the most classical way it appears is in the study of the transport equation. As you know, when you study an ODE, to each ODE, you associate the continuity equation. And what means the continuity equation? You just say that instead of studying the ODE, you take the initial data, you take some, the initial data is some function times the Lebesgue measure, and then the transport equation is just the evolution of this density. And somehow the Lebesgue measure is supposed to be there. You somehow, from the very beginning, anticipate that the Lebesgue measure is absolutely continuous, is quasi-invariant by the flow of your ODE, which in finite dimension is somehow clear. And but what I would say is infinite dimension, it's not so clear because there is no reference measure which is so canonical. And then even this starting fact is not clear. And somehow what we study will be transport equation in infinite dimensions, and you just say that you have some nice reference measures. And so that's why, in fact, also if you take all these problems like Vlasov-Poisson and other PDEs are in fact questions of transport of measures. Right? But of course, this is the PDE perspective, but from probability viewpoint, it was also a question people asked, and actually there are two basic theorems. One is the Cameron-Martin theorem, and the other is the Gersonov theorem. And these two theorems are important in probability theory, and the question they really deal with the question of how probability measures behave under transformations. And so let me now state the Cameron-Martin theorem from 1944, which can be reformulated very nicely, very easily in the context of my measure mu s. So normally I defined all objects needed to understand this statement. So let us fix f in H sigma. So H sigma is the big space. So sigma is smaller than s minus 1/2. Okay, so f belongs to the big space H sigma, and let mu f, I denote by mu f the image of my measure mu s under the map from H sigma to H sigma, which is simply defined as a shift, as you need a translation. So as you see, even translations for these questions could be delicate. And they were set out in 1944. And so what we can say is that you take this map. So to each u in H sigma, you associate the shift u by the function f. So you will have the image measure by this map. Actually, each map, this is good with the measures. We have a map. There is always an image measure. And the question is, how is this image measure? And so it happens that the image measure by mu s under this simple shift map is absolutely continuous with respect to mu s, if and only if the starting function is regular enough, belongs to HS. HS is the starting space. And my f is allowed to go everywhere in H sigma, because this is the support, the measure is defined on this space. So this map is totally well defined, and there is a totally well defined image measure. The only problem is that this image measure is absolutely continuous if the shifting function is regular enough. But if it loses the regularity HS, then it is not absolutely continuous with respect to the measure μs. So it becomes a singular measure. And this is a very nice theorem. So how we prove it? In fact, I will go quickly with the proof, because actually I will try to go really quickly. So how we prove it? So at least formally, you can compute the density, because our measure was exponential minus UHS squared du. One can hope that du doesn't change. As you see, my intuition is guided by the expression which doesn't make sense. That's how we work. So in the expression which doesn't make sense, du shouldn't change, but the UHS square, if you put f plus u, you just develop the square. UHS square goes to the du, and you recover the Gaussian measure, and then the remainder, this should be the density. So it should be exponential minus fhs square minus 2 times ufhs cover product. So we see now if f is in hs, this makes sense. And this is the whole point of the positive part of the proof, is to see that μs almost surely this product makes sense, and that's a simple computation. And so indeed, if f is in hs, we don't only know that the image measure is absolutely continuous, we even know the density. The density of the transported measure is given by the expression which I'm now showing. If f is not in HS, why the image measure is not absolutely continuous? It's a very nice argument. You just construct a set which is a full measure, and such that its image is of measure 0. And so you know that it cannot be absolutely continuous. Of course, you cannot say the proof is that this expression doesn't make sense, therefore it's not absolutely continuous, but you have really, I don't have time to discuss this, but there is a very short proof showing that you give a concrete set of measure 1, which is going to a set of measure 0. And this is the proof of Cameron-Martin, and actually Gersonov theorem is something in a very similar spirit, where the only difference is that the shift function f is allowed to be random, but with some very restrictive hypothesis, which makes that the proof I am giving still can work. Okay, this is very quickly explain what Gersonov did, but of course it doesn't mean that it's not important. So let us now see how, okay, we'll see that we have just seen that the behavior, the transport of the measure μs under translations is delicate. And now I will start to study the transport of this measure under evolution, under PDEs, dispersive PDEs, Hamiltonian PDEs. And as I say, this can be seen as a question of studying the transport equation associated with this Hamiltonian PDEs. Which is the Liouville equation in finite dimension. Here I will never write the equation, because I don't know how to analyze it. One day, if somebody develops tools, it would be nice. I just say that what I proved has some consequence on the infinite dimensional Liouville equation. And so the first thing is that we can show that if we take the linear Schrodinger equation, so let S of t be the flow of the linear Schrodinger equation, S of t, and let μs t be the image of μs under the map from H sigma to H sigma, which now instead of doing translation, I make the action of the linear Schrodinger flow. But then it turns out that the measure μs t is the same as μs. It means that it is invariant measure. So my measure μs turns out to be invariant under the linear Schrodinger flow, which means that if I take time t, I transport the measure, it is the same. And the proof is written here. So if I take the linear Schrodinger flow on a typical element on the super of the measure, so you also know that the only thing which happens is a Fourier series where the Fourier coefficients are the same as the initial data, with the only difference that I add this exponential minus ETN square. And now the key point is that this random series has the same distribution as the initial data series. It means that I just remove the oscillating factor. And this is just because the Gaussian variable exponential minus ETN squared G omega has the same distribution as G and omega. And this is because complex Gaussians are invariant by rotations, and exponential ETN square is nothing than a rotation in R2 in the complex line. So just we use that the complex Gaussian, if you apply a rotation, don't change. And so this completes the proof, because these two objects, of course, from deterministic viewpoint, can be seen as a very different objects because of this time oscillation. But from probabilistic viewpoint, they have the same law, the same distribution. And so this is the big simplification. So you can show that, in fact, for the linear flow, this object doesn't change anything if you're interested by the law of the variable. Of course, the realization is different, but the law is the same. So this is the whole philosophy of the probability theory. When things have the same law, we don't distinguish. And in that way, the measure you evolve it, you don't distinguish. In each time you will observe the same measure. So this is really something which is an equilibrium from this viewpoint. And so here there is an important philosophical remark. Sometimes people saying that if you see things macroscopically from big distance, actually you don't distinguish details. And so here is a typical example for this, because if I fix the sequence, it means that I don't take random data, but I take a fixed deterministic sequence, and I start to take about the behavior of this Fourier series. This may have a complicated behavior depending on the nature of time. For fixed sequence, depending on time. So, you know, there are all these taboo effects. For example, Valeria Banica and Luis Vega study a lot this phenomena. So indeed, if you fix the sequence Cn, it depends on the nature of the time t, how the solution is. And as you know, there are some concentrations for numbers which are with big denominator. In any case, the time t really plays role on the behavior of the solution time t. But the statistical behavior under μs is the same for each time. So if I measure the solution of the linear Schrödinger equation only by the measure μs, for each time I see the same thing, right? So it means that if I have some microscopic viewpoint, the things are completely simple because the initial distribution remains for each time the same. If I start to care about details, it means that I take a particular Cn. Then for each time, the time may play a very important role. And so I know there is a paper by Rodniansky, Kapitansky, which is called, does a quantum particle see the time? And so my answer would be, it depends. It depends what you measure. So if you measure with respect to the measure μs, the answer is no. Okay, so let us now go to the nonlinear equation. So I will try to be quick because you have the coffee break. So under the nonlinear, how μs behave under the flow of the nonlinear Schrödinger equation, because the linear Schrödinger equation, as you see, it's trivial, it's invariant. μs is invariant. And then I always, when I study the nonlinear Schrödinger equation, I try to see what happens if I forget about the dispersive part. And so we have the following theorem. Let S be an integer and rho S be the image of μs under the map from H sigma to H sigma, which is defined by the solution map, where U0 gives the solution at time t of this PDE, which in fact is not a PDE because I didn't put the Laplacian. Usually there is the Laplace here. And so I take the solution map of this equation and I ask how behaves the measure μs with respect to this map. But it turns out that as far as the time is not zero, because for time zero is the identity map, right? The measure, the transported measure by the flow of this simple equation is not absolutely continuous with respect to μs. And so this is a simple equation, but it is not so simple proof, the statement of the, because in fact, it is not so clear how to prove that the transported measure is not absolutely continuous. And actually, the proof is completely different compared to Cameron-Martin. It is based on the observation which says that the time oscillation here are destroying the double logarithm Hitchin double logarithm wall. It is something. Okay, I don't have time, but in a sense, the time flow of this equation destroys a fine regularity property on the support of the measure. Let us say it like this. Actually, this is obtained in a work with Tadahiro O and Philippe Soussoe with 4 replaced by 2, but it doesn't change too much. Actually, this precise statement is not written in the literature. It's written with 2 here, but you can put any power. It works equally well in a paper published in Journal of École Polytechnique. And if you look at the proof, you will see that it's not so trivial to prove this statement, but this statement is just saying that the dispersion should play a role, because if I forget it, just the measure mu s is not mapped to absolutely continuous measure. And as you see, we see a huge difference compared to propagation of regularity. The HS regularity, you can propagate it by this equation, but the measure mu s is not well propagated, so it's much finer question. Okay, sorry, I don't do. And now I can announce my main theorem, which is actually a work with Nikolay Tzvetkov and Fabrice Planchon. We can show that, in fact, if you take mu s to be the image of mu s, the image of mu s under the map from H sigma to H sigma defined by the flow of the nonlinear Schrödinger equation with quintic nonlinearity. I take quinting somehow for the same reason like in the talk yesterday by Michele. It is because I don't want to be in the integrable case where there are other methods. So it is a typical nonlinear Schrödinger equation which is not integrable in 1D. So if I take the image map of my measure mu s, I defined in details in the beginning of the flow. In the beginning of my talk, I defined the measure mu s. So I take the image of this measure by the flow of the nonlinear Schrödinger equation, and we proved with Nikolay Tzvetkov and Fabrice Planchon that the image measure is absolutely continuous with respect to the Gaussian measure. And in fact, we can prove similar results for fractional NLS in 1D, for the nonlinear wave equation up to dimension 3, for the generalized KdV equation on BBM time equation. So it's not restricted to this equation. I've chosen this example just because it's simple to state. But it proves, we can prove this kind. We now have methods to prove these results to many equations. And depending on the equation or the situation, we have more or less information about the result in Radon-Nikodym derivatives, because the measures are absolutely continuous. We have some density. We can say more or less things about these densities. And this, of course, gives some information about the corresponding transport equation that in infinite dimensions I don't even discuss. And I am interested, as you see, for the Schrödinger equation, for the moment, we only have methods in 1D, because for some reason I don't have time to explain. And for wave equation, we can go up to dimension 3. So somehow, and dimension 4 is not reasonable to expect that it is true. But in NLS, we still have to solve the problem in dimension 2 and 3. And I think it's just a question of time. But of course, question of time and new ideas. So I'm presently very interested to extend this result to the 2-dimensional NLS. So this is a good place to say. So I can enter a little bit in the methods we use, but I think that I really will be out of time. So maybe it's a good place to stop. You hear me, Vladimir? Vladimir?
Thank you, Nikolay. And have in mind that this is not correct. We started 20 and something more than minutes before. If you need a little bit more to explain, some 5-10 minutes, I think this is reasonable. I already sent a message for the coffee break that we shall shift
okay, so
a little bit.
Thank you very much. If you give me 5 or 10 more minutes, I can go a little bit in the methods, okay? Is it okay, or I don't want to over?
Exactly. This was the invitation because this is, I said, not correct. This you have time at least to explain something. We cannot cut the because of
no, but now
break.
it's a good place. But okay, I continue. So
Yes,
as I
please.
say, I will try to go quickly about the methods. So to prove this kind of results, as far we have two methods. One method is the method basically using time oscillation, or if you prefer, dispersive estimates. And the second method is based on the random oscillation of the initial data. And in both methods, we do not study directly the evolution of the measure μs, but we truncate the measure with some density, with some corrections. And we actually study the evolution of a measure which is defined as some truncation by the Hamiltonian and some density. This is the very important correction, which comes from the Hamiltonian structure, and somehow it's really the art is to choose this correction in a nice way. And actually, I go back to my formal definition now to develop some formal computation. So if I write this measure in the formal way, you see that in fact I can incorporate the correction RSU to the HS square and develop a kind of higher order energy times du. And so somehow, as you see, actually the measure I study is not really the Gaussian measure. I put the correction which comes from the nature of the equation. So this is a way to see the measure. And in fact, now if I take phi t to be the flow of the PDE under consideration, so formally my measure was this one. And when I apply the flow phi t, H is a conservation law, so H of phi t of u is equal to H of u. Because of the Hamiltonian structure, du doesn't change. The only change is in this modified energy. If it was conserved quantity, it also doesn't change, and we have invariant measure. But now, since it changes, the whole point is to choose it so that it changes as less as possible with respect to a true conservation law. And so what I can do is that I simply add and subtract the energy in time u. And so at least formally, so I don't have probably time to go quickly, but at least formally, you obtain that the transported measure is the measure I started with times exponential minus the energy Es in time t minus the initial energy. Why it is so simple? Because chi of H is a conservation law, and I use somehow the mega theorem that the du is invariant by the flow because I will use the Hamiltonian structure. And so therefore we can hope that the random Nikodym derivative of the transport of rho s is simply given by this formula. And this formula is very nice. Es, I recall you, it was in the previous slide, is HS squared by some lower order term. The big problem is this HS square, because HS on the support of the measure is infinite, as I say, and even HS minus 1/2 is infinite. So both terms in this difference are strongly diverging on the support of the measure. This is why these problems are difficult, because actually the expected density is exponential of the difference of two expressions, and each expression is strongly diverging. So actually, in the very beginning, it looks even hopeless to make sense of this expression on the support of the measure, unless something very non-trivial happens. And what has happened is some cancellation between the two terms. And here, of course, the PDE, it becomes a PDE problem. Okay, up to now it was more probabilistic things, but here making cancellations is we use deeply PDE smoothing estimates, and that's why it's no longer a probability problem. It becomes really a PDE problem. How to design these energies Es so that in this difference I capture smoothing. And this is, of course, fortunately in dispersive PDEs is 30 years, there was a lot of progress, and now we will start to use this kind of progress. And in fact, if we go a bit more quickly, how we do it, we just write this difference as the integral of the time derivative, And if I call the time derivative of the energy, as you see, I use really some modified energies, like in the I method or other methods like this. So this modified energy, I take the time derivative. And so if we can, so we will be done. Okay, this is true. We will be done if we can prove that this integral of the time derivative is bounded by constant, which depends only on the energy times h to s minus 1/2 minus epsilon to some power theta with a suitable number theta. You see, this is a smoothing estimate because the energy Es is on Hs level. And I just to ask that when I make the difference between the energies in time t and time 0, I gain somehow 1/2 derivative. And this is, of course, not trivial. And that's why this method is complicated, in fact, and it doesn't work always. For instance, we can do it only for 1D, for NLS, because I require 1/2 gain of regularity. But if I can prove this, we are done. And then even we have some classification. If this number, the power of the Hs minus 1/2 is smaller than 2, then we can really prove that this is the Radon-Nikodym derivative. That's, for instance, what we did in a recent work with Nicolas and Fabrice Plachon. And if theta is bigger than 2, we proved in another work with Giuseppe and Renato that, in fact, we cannot justify probably this density, but we can justify a slightly modified density. And then theta can be as large as you want. So as you see now, we become in some numerology, things like this. There are different methods, different situations. But what I would like to say is that if we would like to go further, we should improve this estimate. It's very naive estimate. I think that we should replace this with more subtle estimate using in a more involved way the probabilistic effect. But of course, I think this is the way where we can go to new results. So this, of course, is true, but I think this estimate can be replaced by more subtle estimate. And hopefully in the future, I will give you talks with this kind of developments. Then the method 2 is different. The method 2 is only exploiting random oscillation of the initial data. And here is a method actually we developed with Nikolay Tzvetkov for invariant measures for the Benjamin equation. And we just use it for this equation. In this situation, because, but we do the same. So in a sense, in this method, I will not use the time oscillation. I will not make this integral from 0 to t and take time derivative of modified energies. I will just reduce the things to t0 and exploit the random oscillation of the initial data directly. So this method is somehow more naive because it just goes to time 0, but it's very efficient. It can use the multilinear, the random oscillation in a more subtle way. And that's what we can do. So how would we do it? We just say that we take a set A, and we will show that if a set A is of measure 0, the transport by the flow of this set stays of measure 0. I don't look for the densities. I don't know how to justify the densities. I just will prove that 0 measure set goes to 0 measure set. As you see, this is the most basic thing, and it simplifies the things. That's the point. Somehow, in probabilistic literature, results are always aiming to identify also the density. I don't do anything in the densities. I only work with the sets. This is somehow which makes the method more flexible. And then what we do is that, okay, I take this measure set and I try to see how it evolves by the flow. So I should study DDT of the transport of the measure of the set at time t bar, which is not 0. What is nice is that this is trick which goes back to Liouville. It says that, okay, if I look at DDT at time t, I can reduce it to time 0. And the price to pay is that I don't look at the evolution of the set A. I care about the evolution of the set phi t bar A. It's a different set. But what is nice that in this method, we immediately replace this set with the whole space. So no matter where the space go, in the next line, in this inequality, I just forget on which set I am when I write the derivative of the modified energy and T0 in some LP with respect to the measure ρs, which is written there. So this object now only takes the flow at time 0. But in time 0, my initial data was the random series. So this object now is suitable to be analyzed by concentration of measure methods, probabilistic methods, no PDE methods, only probabilistic methods. And then if we are lucky to show that this random this multilinear, actually this expression looks very nice, but in practice it's one should compute many things. So this object is actually multilinear expression with respect to the initial data. And this multilinear expression can be handled by hypercontractivity estimates. And actually what we need is to compute the LP norm of these objects and show that it doesn't grow stronger than P. So this is very much like in these Schrödinger inequalities and things like this. And so if I have this estimate, we can formally show that we have quasi-invariance, that 0 measure set goes to 0 measure set. And this is very similar to the uniqueness for the 2D Euler equation. Simply, I would like to show that if my set is of measure 0, it goes by the flow to set of measure 0. So I call rho x of t the measure of the transported by the flow set. So I would like to show that if this function is 0 initially, it is 0 forever. And so how we do it, we just rewrite the inequality 1 as an ODE, which is exactly the same as in the Udovich argument. And so we can just integrate this inequality. As you see, the power p here is fundamental. If it is p to the power 1 plus epsilon, it no longer works. You just write like this the differential inequality, you integrate it, and you just obtain that if the initial data, if initially the set is 0, so x of t is the measure of the transported by the evolution set. So if initially the set is of measure 0, you just obtain that x of t is smaller than ct to the power p. And so if ct is more than 1, you put p to infinity, just like for Euler equation, and you obtain that at least for small times, 0 measure set goes to 0 measure set, and then you can iterate for every time because the constant is uniform. And so this is the formal proof. But then the rigorous proof, again, is not so simple. One should use some stability of the Cauchy problem theory, but of course it's technical. The fundamental idea is written in these 2 slides. And so this is the second method. And so I think that for the moment, the method 2 performs better for equations when the dispersion is weak. And it would be interesting to combine method 1 and method 2, and I explain how. I think that we should incorporate the ideas of method 2 in this integral under 0 t by propagating the randomness of the initial data to larger time. So that's my hope to go further in this problem, somehow to combine the 2 methods. So I hope that if I give a new talk on this subject, I will say that actually there is only 1 method. But of course, it is not done yet. The point is that we should be able to go further in this estimate by exploiting multilinear randomness even for later times. And this will allow to use the both time oscillation and random oscillation. Okay, so thank you for your attention, and I'm sorry for the coffee break.
Thank you, Nikolay, for your interesting talk, full of creative and deep ideas. Now, we shall change a little bit the tactic. First, we shall invite our participants via internet if they have some question, because yesterday we had a little bit less. If somebody wants from internet to ask some question.
Actually, do you see me? I don't know. Or I did some mistake probably.
No. We see you.
Can I ask something?
Yes, we see you. If somebody wants to ask something.
Can I ask something?
Yes.
So in the dispersionless case, so from your result with hero and software, we know that the transported measure is not absolutely continuous. So what I'm curious about is that just in terms of the Sobolev regularity, can we expect some regularity threshold between the absolute continuity and not absolute continuity or singularity of the transported measure?
I'm not sure I get it, your question. In the result with Hero and so there is no regularity restriction.
Yes, just my point is just so in terms of another point of view, just so in the theorem that is in terms of the dispersionless case, but just my question is, so in terms of the Sobolev regularity, so can you think about some regularity threshold between the absolute continuity and the singularity?
I don't think that I see what you mean. You have such kind of regularity threshold for not for the dispersionless case. I think there always you have singularity, but this kind of threshold typically appears if you take, for instance, the result for the wave equation. I believe that there is a regularity threshold when the transported measures start to be singular, but it's a different situation. For the dispersionless case, I don't see what kind of regularity threshold you talk about. You mean starting from some as you are singular and then you become absolutely continuous?
And just starting point is the equation has the dispersion, dispersive equation. It has dispersion, but
it has dispersion.
It has dispersion, but in terms of some regularity, very low regularity.
Yeah.
So can you
but I didn't talk about this in my talk, but yes, that's what I expect. For instance, in the three-dimensional wave equation, or even in two-dimensional wave equation, we have some absolutely continuous regularity result, right? With Hero or in higher dimension with other people. And I believe that in this situation, if you start to take less regularity, the transported measure will no longer be absolutely continuous. But we don't have, actually, we know it. If you take, we see it already on the level of the Gibbs measure. As you know, the Gibbs measure starts to be singular with respect to the Gaussian measure in 3D, yes, for instance, right? But then if you start to take higher regularity, at some point it will be absolutely continuous. And I believe that this will be also the point where in this construction you will see that we will no longer be absolutely continuous, but what will be absolutely continuous will be a shifted measure, right? Which will be somehow the higher regularity analog of the Gibbs measure. Okay, maybe that's something I believe is true. So if you take, for instance, a three-dimensional wave equation, I believe that there is some regularity up to which the transport is absolutely continuous. And then starting from this regularity down to the Gibbs measure regularity, there will be some measure which is a shifted measure, which is not absolutely continuous, but which is not so different, just to make a shift. And this measure will be absolutely continuous. Okay, so I don't know how much I'm clear, but no, is it clear or not?
It was nice explanation.
Okay, I can give you more details if you wish, but I have a clear idea what should happen. And indeed, in some cases, the measures which will be absolutely continuous will become, in some sense, non-linear. They are not really not linear, but they will not be the Gaussian. They will be a shifted Gaussian measures.
Yes.
Exactly as for the Gibbs measure. You know, but the three-dimensional Gibbs measure, it's not the Gaussian measure, but it's in some sense almost the Gaussian measure, in the sense that you should shift it with some random vector. Exactly as in Radom Nicodim, right? In my talk, in Cameron Martin, you see, if my vector f is in HS, it was absolutely continuous. It has a lower regularity. It is not absolutely continuous, but it is still close to this measure. So I believe that for low regularity situation, the quasi-invariant measures will be a random shift, will be the measures which are obtained after a random shift of the Gaussian measure, and these will be quasi-invariant. and they will be singular for the same reason as in the Cameron-Martin, the shifted measure is singular. And this reason, in fact, is not so, for me, it is not so different from the Gaussian measure. Of course, mathematically, they are not absolutely continuous, but it is much less violent than what we do in the result with Sobolev. It's really much more singular, I think, in a sense. Okay, I'm sorry, I stopped here because I can't speak even more. So the answer is yes. I believe that regularity will make that the quasi-invariant measure will be different. Will become singular with respect to the Gaussian.
Okay, and probably we shall ask the people from Aula if there are some questions, observations. For the moment, no. So let us thank the Nikolay again for the important, interesting talk.
Okay, thank you. Enjoy your coffee break.